We have the characteristic polynomial of a matrix A, and we want to deduce the characteristic polynomial of its inverse. If the size of the square matrix A is n, then the degree of the polynomial is also n. So we can write the characteristic polynomial of A is an x power n plus an minus 1 x power n minus 1 plus dot 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 plus a1 x plus a0. The polynomial is unitary. That means that always an is equal to 1 and a0 is equal minus 1 power n for determinant of A. The characteristic polynomial of A inverse is given by 1 by a0. a0 is the last coefficient here, and then I keep the same coefficient here, but the power of x are increasing. Here the power of x are decreasing, here the power of x are increasing. I give an example to a square matrix A equal 1 0 3 2. I calculate the characteristic polynomial of A using the formula PA of x is equal a squared minus trace of A x plus determinant of A. Here I see that the characteristic polynomial is unitary. That means that the coefficient of x2 is 1. So I calculate the characteristic polynomial. x2 minus trace is the sum of the diagonal entries. 1 plus 2 equal 3. And then the determinant is 1 times 2 minus 3 times 0 equal 2. Then the characteristic polynomial of A inverse is 1 over a0. a0 is equal to 2. 1 over 2, and I keep the coefficient here 1 minus 3 and 2, but with decreasing power of x. 1 x power 1 here and x power 2 here. I do the product and rearrange the polynomial, so I get P A inverse of x is equal x power 2 minus 3 half x plus 1 half. I verify using another way, so I calculate the inverse of A using the formula of the inverse of a matrix square size 2. So A inverse is 1 over the determinant. The determinant of A is 1 times 2 is equal to 1 over 2. Then I switch the diagonal entries 1 and 2, 2 and 1, and then negate the off diagonal entries 0 0 here minus 0, 3 minus 3. So 1 over 2 times 2 is equal 1. 1 over 2 times minus 3 is minus 3 over 2. 1 over 2 times 1 is 1 over 2, and here 0. So I use again the formula giving the characteristic polynomial. So is x2 minus trace of A. Trace is 1 plus 1 over 2 is 3 over 2, and then the determinant of A inverse, 1 times 1 over 2 is 1 over 2. So I find the same results. I calculate the characteristic polynomial using two different ways. So check out. Now here is the proof. The characteristic polynomial of a matrix A is by definition the determinant of xin minus A, where In is the identity matrix of size n, which is also the degree of the polynomial. So I can write the polynomial as an x power n plus an minus 1 x power n minus 1 plus dot 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 plus a1x plus a0. Here, when I develop the determinant, the coefficient of x power n is 1. So an here is 1. And when I evaluate the polynomial in 0, x equal 0 here, so I get here determinant of minus a is of size n, so determinant of minus a is minus 1 power n, determinant of a. And if I put 0, x equals 0 here, all this goes to 0, it remains a0. So the determinant a0, so the coefficient a0 is equal to minus 1 power n, determinant of a. Minus 1 power n, determinant of a, is the last coefficient. The first coefficient is 1. For all complex number lambda, the matrix lambda in minus A inverse is equal minus lambda A minus 1 factor of 1 over lambda in minus 1. This is just factorizing by minus lambda A inverse. If I do the product here, this times this gives lambda in, which is here. This times this gives minus A inverse, which is here. So this just factoring by the factor minus lambda A inverse. Why I choose this matrix? Because the determinant of this matrix is by definition the characteristic polynomial of A inverse. So I would put the determinant both sides. Here determinant lambda in minus A inverse. Here the determinant of a product is the product of the determinant. So I get here determinant of 1 by lambda in minus A, which is the characteristic polynomial evaluated in 1 by lambda. Here instead of x, here I have 1 over lambda. So this determinant is the characteristic polynomial of A, and here determinant of this is minus 1 power n lambda power n, determinant of A inverse, but determinant of the inverse of a matrix is the inverse of the determinant. So minus 1 over n, I can put it on the denominator, it doesn't change, and then in the denominator I will have a0. So here characteristic polynomial of A inverse, here 1 over a0, here lambda n power n, characteristic polynomial of A evaluated on 1 over lambda. Here, this quantity is a polynomial, and this polynomial is called reciprocal polynomial of PA. So we can say that the characteristic polynomial of the inverse of a matrix is 1 over A0 times the reciprocal polynomial of the characteristic polynomial of A. So I replace here 1 over A0 lambda n, and then I write the polynomial A of A evaluated in 1 by lambda. So I get an x is 1 by lambda, so 1 over lambda n plus an 1 over lambda power n minus 1. Then here a1 x, then I1 1 over lambda plus a0. I do this product here, lambda n by lambda n, simplify and give an plus an minus n lambda here, then I1 lambda power n minus 1, because it is lambda n times 1 over lambda is lambda power n minus 1, and here finally lambda n by a0 lambda n. So I find the formula giving the characteristic polynomial of the inverse of a matrix in terms of the characteristic polynomial of the matrix. If I work in complex number, the matrix with a complex entry, then the characteristic polynomial of A is split, and I can write it as the product of x minus the eigenvalues lambda j, where lambda j are the eigenvalues of A. We know that the eigenvalue of the inverse of a matrix is the inverse of the eigenvalue of the matrix. So if I apply this to the matrix A, the spectrum of A is 1 and 2. The eigenvalues are 1 and 2. So the characteristic polynomial of A is x minus 1 times x minus 2, and the characteristic polynomial of A inverse is x minus 1 over 1 factor of x minus 1 over 2.